Um, so in this series, I will talk about how to do the UAV control, which is unmanned air vehicle control. Uh, and unmanned air vehicle is something like this. So in order to learn how to control, the altitude of this flight, we have to learn some basics. The first basics we need to learn is the coordinate frames, which essentially the most important two frames are inertia frame and body frame. Before going into the details, right, I'll show you some simulation. So this flight is flying like that in a so-called northeast. This is up, but usually we use northeast down frame. We'll see that is actually your inertia frame. And if this plane is flying like that, and we want to kind of change directions, change rotations, how can we express that in kind of mathematically? What we do is that we input three parameters called yaw angle, and then the pitch angle and the raw angle. I will talk about that a little bit later. That's called the Euler representation. But right now, let's try to first play with the yaw angle. Maybe let's first play with the raw angle. So if my raw angle is like 45 degree, divided by 180 multiplied by pi in radians, and then let's simulate this. When we run the simulation, we see that the raw angle becomes 45 degrees and the plane changed its position. And then let's again play with the so-called pitch angle, where let's do 30 degree. And then we rerun the simulation. We can see that the pitch is 30 degree and the flight is now pointing up. Similarly, we could change our yaw angle, which is on the horizontal plane. Let's do 50 degree, or more interestingly 150 degree. Let's play. See, the plane actually fly towards us now. So this gives the importance of actually learning about coordinate frames and rotation matrix, right? In this first video, I will start talking about inertia frame and body frame, which are the most two important frames. And why we need to learn about this, one of the reasons is that the sensor on the UAV is usually the GPS, as well as something called gyroscope. And GPS usually gives you a output that is in the so-called inertia frame, which we will cover a little bit later. And then this gyroscope usually gives you information inside the body frame. So we have to actually transfer information between these two frames. This is one of the reasons that we need to learn these frames. And another reason is, of course, we when we use Euler representation, we to describe the plane itself, the UAV itself, we are essentially transferring between the inertia frame as well as the body frame. You will later on see that this angle is kind of defined against the body frame. Let's talk about inertia frame. It is called northeast down frame, and it's assumed to be fixed. What does that mean? So essentially, if we have an Earth, right, and then let's say the plane is kind of going, if this is the center of the Earth, and if you're pointing this vector up, and this is the so-called altitude of the plane. Imagine if your plane is like flying somewhere here, right? So this is like the altitude of the plane, describing how high it is from the ground. And this point here, if we define a so-called inertia frame, it is always like pointing towards the North Pole, which is north, and then to the east frame, and then the z direction is pointing down to the ground, to the center of the Earth. So that frame is essentially called a inertia frame. And why it is fixed? It is because when this plane is flying, its speed, or the instant, the time of duration, or the interested frame of the time is so short that the self-rotation of the Earth and the rotation of the Earth against the Sun can be all ignored. And also we can also assume the Earth is actually a flat ground, because your plane is not like flying across the Earth in an instant. So when we talk about inertia frame, we assume that this is like pointing down, and then to the north and to the east, right? And we assume that this frame is kind of fixed. The Earth is not rotating, and everything is fixed. So that's why we call it fixed frame, or inertia frame, or northeast down frame. And as a contrast, what is the body frame? Body frame is a frame that attach with your UAV, with your plane. So body frame, on the other hand, this is like your X pointing from the nose of the nose of the plane, and then of course the Z axis is like pointing downwards. And we use actually I for X and J for K for Z, and in the a lot of books they use J for the Y. There's one question to ask. Do you think the Y is actually in this case usually it's from, because usually the wings of the plane is like perpendicular to its nose. So do you think the Y is like that, or the other direction? That actually leads to another concept called the right-handed frame is, no matter it is an inertia frame or it is a body frame, it is a right-handed frame. What do we mean by right-handed frame? Right-handed frame is essentially if you use your right hand, your index finger is your x-axis, and then your middle finger is your y-axis, and your thumb is your z-axis. So if you match this with like the northeast down frame, right? Your z is actually your d. Your z is your d, and your x is actually your north, right? Your east is then your y. So this is your y, this is your x, and then again the notation is used kind of alternatively. So y is j, x is like the I, and then d could be the k. So similarly, you could use the right hand frame to charge. If this plane is flying like that, my index finger out of the nose is like my x, and then pointing downwards is the z, and you can see that if this plane has a wings, the right wing, from my side, the left and right, the right wing will be its y. So we draw it correctly, and this x, y, z of course is orthogonal to each other, so it's like 90 degree from each other. Similarly, here is 90 degree, 90 degree, and 90 degree. So that covers basics of inertia frame and the body frame. Of course, if your plane kind of fly in the other direction, your body frame is not a fixed frame, so the frame actually rotates together, with the plane. Maybe the drawing of the z here is a little bit confusing, but essentially the z should be pointing actually perpendicularly down. You got the idea. So those are the two most important frames used in aircraft control. Thank you very much, and next video will cover, actually before I left, I also want to cover the right-handed rotation, which is related to the right-handed frame here. So using the inertia frame as an example, if I say I rotate against my z-axis and I do a right-handed rotation, what I mean by that is you use your right hand, your thumb is pointing to the z-axis in this case, and then your right hand will do a rotation like that. So this is the positive direction of your right-handed rotation when you rotate your frame against your z-axis. This is called a 2D rotation because your z-axis is kind of fixed, and then we just rotate things on the horizontal plane. Similarly, you could do right-handed rotation against your y, right? In that case, your thumb is pointing to the y direction, and in this case, the vertical plane here will rotate, and its positive direction, of course, is defined in this direction. So that's why right-handed rotation is also important, because it essentially define the positive direction of the rotation. With that being said, next video I will cover the yaw pitch yaw, as well as the rotation matrix how to represent a 3D rotation using the Euler angles, which is essentially yaw, pitch, and roll. Thank you very much.